Welcome back to the podcast from Responsible Raw Materials. Today, I'm joined by Professor Byrt and Dr. Samantha McGaughey from the Australian National University. Caitlin and Sam are plant biologists, but don't let that fool you into thinking that this is just a conversation about growing things. Their work sits right at the intersection of some of society's biggest resource challenges, from food security and water management to critical minerals, resource recovery, and the technologies needed to support the energy transition. For much of their careers, they've been studying how plants acquire, transport, and manage the resources they need to survive: water, nutrients, metals, minerals. And what they've discovered is that nature has evolved some remarkably elegant solutions to resource management challenges that humanity is only just beginning to grapple with. In this conversation, we explore how research, originally focused on improving crop productivity and agricultural resilience, has evolved into entirely new approaches to recovering valuable resources from waste streams. We talk about Caitlin's work developing salt-tolerant wheat, now used around the world, and Sam's research into crop productivity and food security, and how both of those journeys ultimately led them into a world of critical minerals and resource recovery. We discuss a fascinating technology inspired by plant biology that could help recover metals, nutrients, minerals, and clean water from industrial, agricultural, and municipal waste streams. But we also talk about something broader. How do we move innovation from the laboratory into the real world? Why do some discoveries transform industries while others never make it beyond a scientific paper? And what happens when researchers from very different disciplines start working together to solve shared problems? What I particularly enjoyed about this conversation is that it reminds us that responsible raw materials isn't just about what we extract. It's also about what we grow, what we recover, what we reuse, and how we manage resources through their entire life cycle. It's a conversation about innovation, collaboration, and learning from nature itself. I hope you enjoy it. Okay, I'm sitting here on some grass beside an old tower in Barcelona with the amazing Caitlin and Sam. But Caitlin, do you want to start? Who are you?
So I'm Professor Byrt from the Australian National University, and currently I'm an Australian Research Council Industry Fellow, which has given me the opportunity to innovate in the space of how we're going to supply the materials of the future.
Amazing. And Sam, how about yourself?
So I'm Sam. I'm a postdoctoral research fellow at Caitlin's group at the Research School of Biology at ANU.
So Caitlin's your boss, is that right?
Yes, and a very good one.
Well done. Excellent. Caitlin is now looking suitably embarrassed. So Caitlin, let's start with yourself. So what is it that you do on a day-to-day basis?
Well, I've had this amazing opportunity over sort of a 20-year period to study how plants take up and separate different resources, so water, nutrients, metals, minerals, and our team get to look at like the actual molecular mechanisms that do that in nature. Initially, it was all agriculture funded because that impacts food security. So everything was resourced by agricultural companies to support that work. But then we realized that some of those mechanisms that plants have evolved to transport the critical metals that we need for humanity's energy security can actually be applied to innovate technologies that will help us with sustainably managing those resources.
Amazing. So if we go back sort of through the agriculture side of things and I guess into biology to start with. So what got you interested in that to start with?
It was definitely thinking, like, as a kid about the trajectory. I thought about how many people, what do all people need, what do all people use, what impacts does that have? And early on, I was like, oh, no, it doesn't add up. It doesn't add up. It's not going to work. And so I think that drove me to be like, well, the only way to figure this out in terms of, having communities where they're actually living well is to come up with innovative ways that we can do that.
So Sam, do you have a similar story or are you a little bit different?
I guess I'm similar in that during primary school and high school, I knew that I wanted to do something that would help people, but I didn't necessarily want to be a doctor or work with animals because I'm a bit of a soft touch. Um, so I thought, well, I love biology, and I found plants really interesting, and so to go into that agricultural space to try and, yeah, I guess improve crop productivity, improve food availability, yeah, was something that I wanted to do.
So let's talk about that crop productivity, because of course crops, etc., produce raw materials as well. What's some of the work that you've done in that area?
So my PhD was looking at a class of transport proteins that had recently been identified to transport water and also different salt ions. And so I was looking at how those transporters might impact crop tolerance to drought or to really saline soils. And then my first postdoc after my PhD was with the C4 Rice project, which was a Bill and Melinda Gates Foundation funded project looking to improve the photosynthetic efficiency of rice, particularly for use by smallholder farmers.
And have you seen any of that research now being used around the world, or is it sort of still in that research stage?
So for the C4 Rice project, I mean, there's been so many pioneering discoveries that have been like fundamental discoveries that have been generated through that funding, which has been it was such an incredible opportunity to be part of that consortium. And we're definitely getting close to making those photosynthetic gains and productivity gains in rice.
That's brilliant. And Caitlin, how about yourself?
Well, during my PhD, we were looking at salinity tolerance of wheat, and in that project, the time frame at that stage, so that was around 2005 onwards, it took a good decade to get from the stage of, oh, okay, this wild wheatish-like plant, which is super salt tolerant, how does it do it, and how do you move that into a modern cultivar and actually make that productive? And that was successful. So we figured out what mechanisms the plant was using. We managed to cross them in. We managed to develop wheat that was more productive in saline soils, and that was patented and is used in like 11 countries around the world. So it got out there. And yes, it did take a long time, but at the same time, that was through an era where the tools in the kind of space that Sam and I work in were really in their infancy as well. So the sort of tools that we have today in terms of biological engineering are amazing. So now you could just knock that off so much faster. So it's like the era of the biotechnological revolution.
I'm loving that. So, in terms of, I mean, congratulations with regards to getting that research out there across 11 countries, etc. How did you actually get that to work? Because again, so much research kind of gets stuck before it can get out there and make a real difference.
Giving it away for free. Serious, like I mean, I didn't make any money off that. Like it was supported originally by some industry grants and some taxpayer funds, and then it was patented, and then it was gifted, and then people can use it.
And do you see that appetite for giving something away for free? Is that common?
Well, right now we have this bit of a catch-22 situation because if you do all this amazing innovation and you just write it up and put it in a paper, that doesn't deliver it to people. That does not deliver it to the real world. And then the way that the structures in society work at the moment for taking an innovation from baby stage all the way through the TRLs to delivery for society, they ask you to kind of keep it a secret, keep it value, make sure the value's in there, commercialize it. And so that prohibits giving it away for free. So I think we've got to figure out, within our communities, how can we stop losing amazing innovations at that stage because of that structure being incompatible with really delivering for the world?
So, Sam, do you think this is something where we need different mechanisms for being able to get that research out there?
I think definitely for deep tech, because it is, I guess, such an expensive and time consuming endeavor to take something, from that initial concept through to delivery. And I think, I guess, our experience sort of dipping a toe into different commercialization spaces, I do get a sense that there is an overwhelming appetite to find the unicorn, but maybe it's okay to not be a unicorn and maybe be some kind of other quadruped that is just fine. Um, so I definitely think there is some, yes, hopefully we can figure out different ways to do things.
So thinking of different ways of doing things and thinking about different quadrupeds, I'm loving that. So I guess fairly recently you've been making this move from living things into the world of rocks and minerals and metals and things like that. How have you found moving into I guess what's like a slightly different discipline space or a different realm of scientists and researchers who are working together?
I guess it's been really heartening to see just how passionate people. I mean, obviously, I know that there's a lot of passionate people in science in general and in plant science. I would count us amongst them. But also to see how invested people are in wanting to do things better, having more of an environmental focus or having more of a long-term view. Um, yeah, I think has been really wonderful. And then, of course, we're learning a lot, um, which is always really fun.
What are some of the things that you've been surprised by?
I learnt what a melt was, which yeah, I hadn't really. Yeah, and the distinction between a liquid and a melt, which seems, I think, a little bit controversial. Um,
I'm loving it. All of the trigger points with regards to geochemists, etc. Caitlin, how about yourself?
I think you we say that some of the big innovations are going to come from the space between disciplines, right? And that having disciplines siloed limits us. And so what I really love about, being able to connect with people in the geochemistry type space is that they have been really welcoming. They've been willing to step outside their comfort zone, just as it's a little out of our comfort zone to try and absorb the sort of information that comes out of a different field. You've got a situation where each field of science has its own language, and so it's like trying to learn another language, and that's really hard. And sometimes they'll use terms in one field that mean something radically different. So, for example, people here are referring to the genetics of the rocks, and as a biologist, we're like, nah.
Is it offensive?
No, it's just it does actually help to describe what they're talking about. But at the same time, then when you get into the depths of the science, where you've got one term used for radically different things in different fields, you have to be a good communicator to actually really learn from colleagues who are using that term differently.
So thinking about using terms differently. So obviously you're now doing some work in this space. Do you want to tell us a bit about what it is that you're doing?
So our team is working on developing an innovative technology which is inspired by the function of plants in nature. And essentially that technology is fed with waste from mines or from urban waste or any sort of industrial waste. And it enables that waste to be separated sequentially, pulling out the target resources. So that could be metals, nutrients, minerals, and also pulling out clean water. So it's like a recycling technology, but for liquid wastes.
And how is the research going?
Really great, actually. So it was, like a high risk thing to embark on. We could have found that trying to, borrow how plants do it doesn't work in an inert technology, but it does work. So the structures that nature has evolved to enable living organisms to harvest these critical metals for their own energy biology do actually work when you build them into a technology.
So in terms of let's look at the metals. So in terms of the metals that you're hoping to be able to extract from that waste, are you targeting specific metals that you think will work better?
Yeah, so we've been given a list of priorities that we're working through at the moment, and we've made some really great progress for the metals. But we also have, I guess, a different aspect of the technology where we're looking at nutrient recovery from wastewater as well, which has also been very exciting and sort of learning from each.
So in terms of nutrient recovery, is that sort of nutrients that might then be able to be, I guess, sprayed back onto fields for crop growth, etc.?
Yeah, so we would be looking at recovering things like nitrogen or phosphorus, potassium, so those three big macronutrients for plants from municipal waste or urban waste, and then generating a recycled nutrient fertilizer product that would then be able to, I guess, maybe have a more reliable source of nutrients for agriculture.
Yeah, because I think there are a lot of pinch points at the moment, shall we say, with regards to where that fertilizer is coming from. And coming from a farming background myself, I know that there are ongoing conversations with regards to when should we be buying fertilizer for the next year and how much should we get, and is that too big a risk? So how quickly do you think you might be able to get this technology out there?
Well, the lab prototypes are looking really, really promising. And then one of our challenges actually is having those partnerships with the industry where they're happy to support us to get on their site and try it on their site. So that's been quite hard. In some cases, we've had to make fake synthetic waste in the lab and test our prototypes on that because it's so difficult to just actually get waste. I know it's an uncomfortable thing for an organization to talk about, to say, oh, okay, we do our activities and whoops, we make all of this waste. So it's not, sometimes we have to sign non-disclosure agreements if we're even going to be given a recipe for the sort of waste that's coming out of industries. But I think to, move towards responsible waste management, we just need to get in there, get dirty and get their waste.
So, in terms of the types of waste that you are looking for, because of course that means very different things in different spaces. Sam, what's your ideal waste?
I think any kind of liquid waste that anyone makes that they think there could be something valuable in there.
So we're not just talking waste that might come from a mining processing operation.
We're waste agnostic. So we could do like waste from piggeries, from dairy, from aquaculture. Yeah.
So then thinking beyond the world of minerals and metals and the world of farming, so there's a lot of focus at the moment on wastewaters that might contain, things that have gone through people. So different pharmaceutical products, etc., which of course then isn't necessarily great for different ecosystems. Is there the potential for the technology that you're building at the moment to be able to look at those aspects, or is that a different phase?
Well, the principle of what we're building is looking at nature and going, how does nature deal with it? And then borrowing that. And so there's different aspects of nature that deal with different things. So in some cases, some molecules will be processed by some organisms and other molecules by other organisms. So I think that the principle applies of what waste we create, there is likely to be capability to deal with it. But I think what we're working on has like a particular specialty in terms of the nutrients and metals and minerals. And that's because plants need them. So anything that plants need, they've been forced through evolution to figure out a solution of how to manage it.
And I guess plants have never really needed ibuprofen.
Not that I'm aware of.
That would be a discovery, wouldn't it? Okay, so moving into the future and thinking, okay, so over the last 20 years, there's been huge changes within the fields of research that you've both been working in. What do you anticipate might be some of the big shifts or changes that are just around the corner, or perhaps we might be encountering in say 10 years' time?
I think for me, as an early career researcher, I think one of the things that I've found most challenging that I think, we are starting to shift in our ways of thinking is that I guess there's an expectation for somebody to follow a more traditional academic pathway, and there are certain metrics that you are, I guess, judged on for whether you're successful or not in that career. And as somebody who's been primarily employed on industry projects trying to do tech development, it's not necessarily a publication heavy area, and that is one of the metrics. But I think the value of having a range of different career paths, a range of different experiences, I think is starting to be valued a lot more, which is very exciting.
I think that if you look through human history, we have had various waves of innovation, and we've also had various, I guess, times of different power distribution. And so what I'm interested in going forward is how well humanity can actually coordinate itself to figure out how to make things better for the many, right? Like, what do we need to do to make things better for the many? And I think that the sorts of innovations in the energy generation and supply space are so crucial to this, but we have to find a way to do it that actually makes people's lives better.
I think that is an amazing place to finish our conversation. Caitlin, Sam, thank you so much and good luck.
Thank you.
Thanks.
So that was my conversation with Caitlin and Sam. And what I find particularly inspiring about this discussion is that it reminds us that innovation often comes from unexpected places. When people talk about the future of raw materials, the conversation is often dominated by questions of supply and demand. Where will we find enough critical minerals? How will we feed a growing population? How will we secure enough water, energy, and resources for future generations? What Caitlin and Sam remind us is that another question is equally important. How can we use what we already have more intelligently? One of the themes running throughout this conversation is that nature has spent millions, if not billions of years solving resource challenges. Plants have evolved ways to find scarce nutrients, manage water, and separate useful materials from their environment. And what's fascinating is that many of those same challenges are the ones that we are grappling with today. Whether we're talking about recovering nutrients from wastewater, extracting critical minerals from industrial waste streams, or improving agricultural resilience, the underlying challenge is remarkably similar. How do we use resources more efficiently? Another thing that really resonated with me is how this conversation blurs the boundaries between sectors. Often we talk about agriculture, mining, water, energy, and waste as though they are separate conversations, but they're not. They're all connected. The nutrients that support agriculture, the minerals needed for renewable energy, and the water that flows through both systems, and the waste produced along the way are all part of the same resource story. And I think one of the biggest opportunities we have over the coming decades is to become much better at recognizing those connections. I also found the discussion around commercialization really interesting, because the world doesn't suffer from a shortage of good ideas. The challenge is getting those ideas out of the laboratory and into the real world where they can make a difference. Ultimately, innovation isn't measured by papers or patents. It's measured by impact. Whether people's lives are improved, whether resources are used more responsibly, and whether environmental outcomes get better, and also whether society benefits. Finally, what gives me optimism is the willingness of people like Caitlin and Sam to step beyond the boundaries of their own disciplines. Some of the most important breakthroughs don't happen within a single field. They happen when different fields come together, challenge each other's assumptions, and start learning from one another. For me, that's one of the most powerful messages from this episode. The future of responsible raw materials isn't just about finding more resources. It's about understanding them better, recovering them when we can, and using them more wisely. And sometimes the solutions we're looking for may already exist in the natural world around us. And that, ultimately, is what responsible raw materials is all about. Thanks for listening, and I'll see you in the next episode. Responsible Raw Materials brings together diverse voices from across industry, academia, government, civil society, and beyond. We explore shared challenges and opportunities that go well beyond minerals and metals alone. We also curate a growing library of hundreds of talks, resources, and insights, free to access and designed to support learning, informed decision-making, and shared understanding. So if you want to find out more, please feel free to explore all our resources at www.responsiblerawmaterials.com.